Hello, hello. Good afternoon, good morning, good evening. Thanks for joining our session. My name is Guillermo Ruiz, and today we're going to talk about how we build a Raspberry Pi supercluster using Postgres on Kubernetes and all the journey we've had till today. It's been like 8 months of project, and I would like to introduce you to the team. Today is not Jorge Solorzano with us. Jorge is a software engineer on Ongres, the company that created a solution that we will be deploying today that is called Stackgres, Postgres on Kubernetes, and myself, which is Guillermo Ruiz, and I'm senior developer for AWS. Before we start in this journey, I would like to give thanks to a person and a project. This has been inspired by Chris Benson, who is the guy that built the largest Raspberry Pi cluster that we know of with 1,000 Raspberry Pi cards, and also Los Alamos National Laboratory, which they had back in 2010. Moreover, a 750 Raspberry Pi cluster that was divided in 5 clusters with mounted in racks, each one with 150 Raspberry Pis and everything integrated. It was such a big project that caught our attention, and we came and said, why don't we build a Raspberry Pi supercluster? Why we did this? First of all, it's supposed to be affordable computing, and we will see as we go into the session that is not the case. It's much cheaper than having big servers out there and a lot of compute, but even though it's a cost that we need to afford. Also, from an educational and practical perspective, we wanted a hands-on approach for distributed computing, and we've been learning the hard way, to be honest, and you will see it throughout the lessons that we're going to share with our audience today. But also, we wanted to have a real-world application, a live demo of a functional Stackgres cluster running on D63 Raspberry Pi. So, how does it look like? This is the cluster that we built. It's on a Pelican case, and it's a way that we can port it to events and showcase it Meetup and many other places. So why don't we start and say, what do we need to build these kind of projects? First of all, we need a bunch of Raspberry Pi, and I want to give thanks to many people because this has been a friend project, asking friends to lend us the Raspberry Pis. Thanks to Ongres, thanks to the guys from the Brain School, Datadog. They brought a bunch of Raspberry Pis, and we'll see. They were not the latest one. We will be working with a 3B Plus, which is quite a bit old, to be honest, but that's what we had. We also had all the electronics, the PDUs, the fans, all the servers, and you will see that we had to split and increase the number of devices for this cluster, and we had this wonderful Pelican case. But one of the components that was really interesting was the 3D printer, because we use, and thanks to our friends from Prusa Research that led us the MK4 3D printer, we print the bay where we're going to connect all the Raspberry Pis, and even how we handle the fans on the back was 3D printed. From a software perspective, we're going to use Ubuntu 24.04, which is the latest long-term support release of this popular Linux operating system. We will also have K3S, which is a lightweight Kubernetes distribution that is optimized for resource-constrained environments like this one that we're talking about, IoT, and it's easy to install. Also, it requires minimal memory and CPU, but we will see that's going to be also a challenge during our project. The second component is the Stackgres, which is an open source platform for running Postgres on Kubernetes, and it combines the power of both tools. We have PXE Boot. We ran out of money, so we couldn't have SD cards for every single Raspberry Pi in the cluster. So what we're going to do is we're going to boot it from the network and see what happens. We've seen hardware, software, and a lot of hours. Immensely lot of hours to be in this whole thing. Let's start with the engineer feature, how we plan and how we see this cluster coming live. We had a phase of planning and designing of how we wanted to collect and how many Raspberry Pis, which was dependent of the amount of Raspberries that we could get from the friends and the people, but also how we could assemble this into a cluster and using the 3D printers. This is mainly from the hardware perspective. So we got from Unify, we got a couple of switches and a gateway, but we also had 2 USB chargers, each of 40 ports. So the maximum capacity we will have in our cluster is 80 Raspberry Pi. So there are the brackets where we had 3 rows with 21 Raspberry Pis each, but there are multiple pieces on the 3D printed side. We had to print over 84 pieces just to assemble not just the Raspberry, but also the fans. As you can see, we're using 5 fans per row, which takes us into 15 in total for this. Let's take an overall view of the whole specs that we have. Each Raspberry Pi, it's a 3B Plus. We have 63 On CPU, it's a 64-bit quad-core ARM with 1.2 gigahertz per core. We have 250 cores, and we have a clock speed of 302.4 gigahertz. Each Raspberry Pi card has 1 gig, total of 63 gigs in this one, and then a bunch of multiple ports that many of them were not used here. Let's start with the networking. Once we got everything assembled, we have everything in our Pelican case. We started with a flat topology for these 63 Raspberry Pis, meaning that all nodes were directly connected without any hierarchy. To manage the cluster, we implemented a central control plane acting as the brain of the system and was responsible for coordinating tasks, collecting metrics, and ensuring a smooth operation across all the nodes. The network config was kept simple, with all Raspberry Pi sharing the single 300 megs bandwidth, that is what we have with these 3B plus Raspberry Pis, which enabled the communication between the nodes and the central control plane. This setup allowed us to quickly deploy and test the cluster, but it also highlighted challenges like bandwidth saturation and CPU overhead as the system scaled. Here is a bit of how we implemented the structured topology, where we're using 2 switches of 48 ports connecting the 63 Raspberry Pi, and the switches handle the intra-cluster communication, ensuring that low latency connectivity between all the nodes. To provide external access to manage all the routing, we integrated a gateway which connects the cluster directly to internet. And additionally, there are small devices called UCK G2, it's the Unified Cloud Key Generic G2, was deployed to manage and monitor the network configuration. It offers us centralized control and visibility into network performance. As you can see, very simple setup. It provides us a manageable infrastructure for the cluster while we balance communication and internet connectivity. I want to show how it looks like. The Raspberry Pi is connected to different switches. We talk about 2 switches. This is the bottom switch that is organized to port the whole strategy. The idea is to simplify, and you will see that the nomenclature of every Raspberry Pi is coincidence with the port they are connected to. It will help us reduce troubleshooting in case we have problems. As you can see, odd number Raspberry Pi is 135 or connected to the odd numbers ports and even to even. This covered ports 1 to 42 on the bottom switch, and the remaining ports were reserved for key infrastructure components. For example, port 43, we will connect it to the top of the switch, 44 is to the gateway for internet, 45 to the cloud key, and 46 to the Pi server. However, if you want to do it really well, you should know and understand how many ASICs your switch has and try to put the big servers in different ASICs so they have their own bus and their own pipelines to move traffic between things. We place it here in the last part of the switch because we learned by the hard way in the old days when Cisco came with a design that they have the reset button in port number 1. So when you were plugging the cable, you were rebooting the whole switch. So because of that, it took panic and we just deploy everything at the end of the switch. As again, take a look to your ASICs and see where it fits to ensure that traffic goes one way or the other. Here is how it looks on the top of the switch, where we have still available space for new Raspberry Pis. As we mentioned earlier, just 80 Raspberry Pi can be fit in this cluster. Bit of a view of how much traffic we are moving here. As you can see, it's not trivial. We are moving gigs of traffic, even terabytes if we go to the Pi server that is acting as the gateway to get all the metrics and collections. And how does this Raspberry Pi cluster looks like in reality? Because we show a picture at the beginning. Here is a little video of the whole thing running. So let's boot up this whole thing. Let's start with the build. In this setup, as we mentioned, PXE Boot, which is pre-boot execution environment, is used to streamline the boot process for the Raspberry Pi cluster, removing the need for individual SD cards. The process begins when the Raspberry Pi powers on and requests an IP address from the DHCP server. It's supposed that the DHCP server will handle this with specific options. What we've done is we hard-coded the IP address to ensure that they always be given the same IP address. Once the Raspberry Pi receives the predefined static IP, which is configured on the dhcp.conf file, the next step involves requesting the bootloader file from the TFTP server. For the operating system, we use Ubuntu and Raspbian images served via the NFS mounts. To ensure and prevent storage conflicts across the nodes, overlay file systems are used. This allows the Raspberry to efficiently mount their operating system image and share the storage while isolating writes, so we ensure that we have a scalable and manageable boot process for the entire cluster. Here we came with a little bit of how this process goes. The Raspberry Pi comes and shouts, hey, I want my IP address. Which one can I use? We have the DHCP server, the Raspberry Pi server, the NAS, which is sleeping because it doesn't intervene in this process. We have our router coming and say, okay, you have this fixed IP assigned, but now it's okay, but I don't have operating system, and here is my serial number. Who can help me? The router doesn't know because it's not configured for that. So here is where a PXE Boot server will come and will say, okay, here are your boot files for your serial numbers. And then he will ask finally the NAS on, hey, I need storage here. Could you please share it with me? And it will hand over there. Easy process, 3 different devices involved. But to configure the Raspberry Pis for PXE Boot, with the latest one, it's enabled by default, but with the old ones, you have to do it manually. You had different ways of doing it. You could just go and update the firmware, edit the boot config, and ensure that you set up the one-time flag to enable networking boot, which is this 7302, bunch of zeros and A, and then remove the ASD card. Problem is that you need to do it for the 63, so you will have to be doing that 63 times, which is not a very fun way to get things working. To set up the PX server, what we found was there's already out there on the internet, and here's the link from the GitHub, which will help you. This solution, it's designed specifically to run on Raspberry Pi OS. However, to use it on Ubuntu, that was our operating system, we had to do some adjustments as the Ubuntu system structure is slightly different. A key challenges arise with the new Raspberry Pi OS that is based on Debian 12, that is the bookworm, which isn't fully compatible with the PX script. To make it work, we use the older legacy Raspberry Pi OS based on Debian 11, that is a bullseye, which maintains compatibility. And additionally, the current script runs in interactive mode, meaning that it requires the user input step by step to configure the PX server. To streamline the whole deployment for a large cluster like the one we are building, the script needs to have minor modifications to run in non-interactive mode, which will allow the configuration to be automated without manual intervention. This is the way we proceed. Here is how it looks like. We usually just use 3 options, 1, 7, and 8. That is how we install the PX server. We provision, we get things done. Here is a short demo on how this works. Option 1, we just install with the boot capabilities. Option 7, we create the image. And option 8, we just provision the nodes by deploying the prepared operating system over the network. Looks easy, right? We face different challenges even in this first step. First of all is the manual MAC addressing collection. Building this whole thing and having static IP required detailed DH duration, how we predefine the whole thing. We had also initial configuration barrier that was difficult without having a pre-configured network settings. Having this on the PX side just to boot things came, hey, what are the different type of solutions that we can have on this whole thing? There are a few of them. For example, we can manually collect all the MAC address. You check the MAC address from the step 1 where we were enabling the flag. You can just go and do it 63 times to see which class on the Ethernet address you have. But you can also do it from the network switch, just getting the show MAC address table. Remember that we designed the way to understand the nomenclature of each Raspberry Pi, that it's correlated to each port that we have in the switch. So a couple of times you will get the whole thing. As we said, the nomenclature, we use the last octet and the port number of the switch. So for bottom switch would be 1 something, top switch 2 something. If you see, for example, this IP address 172.16.5.105, we will set the Raspberry Pi to 105, which will be located in the bottom switch on port 5. Here is a view from the console on how it looks, the nomenclature of everything what we have installed. And now comes the serial number to provision the operating system. So there were also different options. You could do it 63 times again and just see the CPU info that will extract the serial number. This will read the CPU information, search for the serial line, and it will extract that number. Or we can use the device tree to extract the serial number. What it does here, it reads the serial number directly from the Raspberry Pi's firmware device tree. And you need to have a working operating system and access to the SD card. Again, we didn't have SD cards for the whole thing. So doing 63 times was not really the way to do it. So we went with option 3. We checked DNS mask logs, that is what is using this PXE Boot script that we just deployed. There's some manual work and extraction. You need to manually check the logs, filter the data using tools like AWK and grep, and extract the relevant serial information. This is how it looks. If we look out there, as you can see, this is just for a single IP, so you will have very long logs to get all the 63. So it takes a bit of time, but you can get the IP address with the serial number. So, strategies to tackle all the network issues, because we are sharing just 300 megs for the whole thing there. One of the things we could do is traffic segmentations on the VLANs. We could implement there, for example, we can create separate VLANs for the PXE Boot traffic. That will be something that is used just in the initial phase to provision the whole information on our Raspberry Pis. We also have the Kubernetes communication, that is the server to the Raspberry Pi traffic in our solution. And we also are going to have the Postgres API calls on Kubernetes, which is the data plane communication. So to prevent this, we could probably go and just set up VLAN 10 for PXE Boot traffic, 20 for server Raspberry Pi control plane, and VLAN 30 for Postgres API communication. We can also configure QoS rules. For example, we can assign higher priority to the Postgres API communication and Kubernetes control plane message, which is what is the main topic and what's going to be heavily happening in our cluster. And we can set a lower priority for the PXE Boot and other non-critical traffic. As we mentioned, we're just going to do it one time for the setup, or every time you just need to add a new Raspberry Pi to this cluster. We could also implement IGMP snooping and broadcast storm control on the switches. We could limit the impact of broadcast and multicast traffic on the network. To minimize the number of intermediate switches, trying to reduce the amount of latency that we can have in the whole setup, we could have flow control, which helps manage traffic congestion. We could have flow control that helps us manage traffic congestion by signaling when buffers are full, but also jumbo frames, which increase the maximum MTU unit size. It will allow for more efficient data transmission. Set this to 9,000 bytes on both the Pi network interfaces and the switch can reduce the packet fragmentation and improve throughput. To be honest, didn't have too much impact in our deployment. And then we have also the DNS. Kubernetes clusters rely heavily on DNS lookups, so we can ensure that the DNS caching is configured on both the server and the Raspberry Pi nodes to avoid repeated external DNS queries, which can introduce latency. We can set up a local DNS cache or DNS forwarder on our server to handle DNS requests more quickly. And last but not least, link aggregation, port channels on the switches, trying to load balance across multiple switches there. And to be honest, there's always things that we can just go and upgrade from 1 to 10 gigs and have high-speed connectivity. Now what? We had the assembling of the Raspberry Pi, we have the network under control. Let's go ahead on Stackgres and let's see how this whole thing works. As we mentioned, Stackgres is a PostgreSQL as a service platform that will simplify the way you deploy Postgres on Kubernetes. To be honest, it's just a single command in your Helm chart. You put it there and it will have the whole installation process. I was surprised because I was expecting, with all the problems and challenge we had before, that this was going to be, again, another big challenge, and ended up being the easiest solution. So we had different deployment strategies here. As you can see, we have the running Kubernetes on Raspberry Pi using tools like K3s, or you can even use the K3s soup from Alex Helix that has also another wrapper to make it easier installation. For this one, we will have from sharding with T2s, and it will integrate management of Postgres clusters and all the high availability features that we can find on this database. So here is a bit of the architecture. It's a modular, and let's break down a little bit of the key components. We have a Stackgres controller at the core, which extends the Kubernetes functionality by defining custom resource definitions, or CRDs. The Stackgres controller will act as the orchestrator and manage these CRDs. Kube control is used to interact with the controller, enabling the users to create, configure, and manage the Postgres clusters declaratively using Kubernetes native YAML files. We also have the REST API for the API users. It exposes the REST API for programmatic access and external use. The API users can interact with the Postgres cluster to perform operations like scaling, configuration, updates, backups, or monitoring. Also, the REST API acts as the abstraction layer of the CRDs, so it will simplify the interaction for developer and tools. We have also the distributed log server for observability. Stackgres uses FluentD to collect and aggregate logs. The logs are then stored in Postgres database and enhanced with a timescale DB for time series data management. And we will save it to persistent volume storage, ensuring that it's durable and available for historical logs for later analysis. Then we have the service primary, which is a read-write traffic. This is then responsible for handling the read-write client traffic, and it routes the connections from the primary Postgres instance, ensuring that transactional consistency and data integrity. It's essential for applications that require updates to the database. We have also the service replica, which are read-only traffic. This will route the read-only client traffic to the Postgres replica instances. This setup offloads the read traffic from the primary instance, so it will improve the performance and scalability for read-heavy workloads. And then we have the Kubernetes pods and replicas. Each Postgres instance, including the primary and the replicas, runs within its own Kubernetes pods. Stackgres will ensure high availability and scalability by managing multiple replica pods. What else? We need to introduce the concept of sharding, that it's a technique to horizontally scale Postgres databases by splitting the data into smaller and more manageable parts called shards. Each shard contains a subset of the data and is managed by an independent Postgres instance or replica set. What this does, it will help us to have a better performance for large datasets by reducing the load on individual database nodes. For example, the queries are routed to the appropriate shard based on the partitioning key, which will ensure efficient data retrieval. This will allow us, the system, to handle increasingly workloads without overwhelming a single database instance. As we mentioned earlier, C2s act as an extension to PostgreSQL, transforming it into a distributed database. It splits table into shards, distributing them across different pods. A coordinator node will manage the query routing and parallel execution, ensuring that the queries are directed to the appropriate shard. This architecture allows us to scale of read and write operations, having parallel query execution and seamless handling of large datasets. As you can see, each worker has its own replica. To deploy this whole thing, if you do it by hand, it can take 2 weeks. Probably you would like to do it with Ansible, and will be like 2 months. It's reproducible. However, and sorry for that line, that should be on the Stackgres side. With Stackgres, you have 20, 30 lines of YAML with the whole configuration, and you can just start deploying your cluster. So let's start building. For the Kubernetes setup, we already talked about K3s, which is a lightweight Kubernetes distribution. We found that the control groups or C groups, that is a feature of the Linux kernel, which allows you to allocate resources such as CPU time and system memory for a specific process or group of process, was not enabled by default. So we just enabled C groups, and we're going to use the external etcd instance, which is deployed on the NAS server as a single instance using shared storage. So etcd is distributed. It has a consistent key value store that acts as the brain of Kubernetes, and it will store all cluster configuration, data, state, and metadata. So hosting this externally, we will centralize the control plane statements management, so we ensure persistence and reliability. However, running a single instance means there's no redundancy. Take care, because this must be taken into account when you deploy into production. Challenges. Let's get a bit of the challenges we had here. So we had hardware constraints. Running Kubernetes control plane on a 3B plus is nearly impossible Because of the limited memory, we have 910 megs and underpowered CPU. We're running on 1.2 gigahertz with 4 cores. The Pi server intended to handle both NAS and Kubernetes stacks lacks the capacity to manage the load effectively. Additionally, the lack of local storage further restricts operations, making resource management a significant challenge. We also had all the network limitation. We've been talking around the session of these 300 megs of network bandwidth, which becomes a network bottleneck for data-intensive operations and cluster communications. So this whole thing limited the overall performance and scalability of our solution. As a very clever guy said once, there is no problem in computer science that can be solved by another level of indirection, which means let's just throw more hardware there. We had these servers. We had a Lenovo was using a Ryzen 5, which was a bit old. We had a Slimbook there, a Ryzen 7 with 16 gigs. And let's see how this works now. Let's get our hands dirty. Let's install the K3s server. So here's the command. We're going to curl and install the version 129. I will define the endpoints. The TLS SAN will label the nodes. What's the service controller? What's the node tent? And we will disable traffic, metrics, and health controller. As you can see, we are already disabling monitoring things. And there's a simple reason behind the scenes. There was not enough bandwidth to get the node exporters inside the infrastructure. And we'll see later how this works also. Let's wait and automate this whole thing. As you can see, it can take 2 hours to get the 63 Raspberry Pi, so you can just go and grab a coffee, have a meeting with your manager or peers, and 2 hours later get back to get the whole setup. We got everything deployed, but if we get here and we get our kube control, get nodes, we see that we have several that are not ready. They were flapping, and we were seeing a lot of this happening. We find out-of-memory issues, storage disconnections, high load, and network congestion happening. Also at the beginning, we found that the USB charger that was providing the power to the Raspberry Pi was not working properly, and we had to replace it. It took us some time to find that it was the charger that was giving out all the problems. What's the solution here? Hope that you guys like IT crowd, because, hey, have you tried to turn it off and on again? And it worked. We got things back. And now the easy part. Let's get on the Stackgres solution. So this command will install or upgrade the Stackgres operator in a new namespace with Prometheus and Grafana turned off. Again, things that are monitoring and observability, we were running with the basics to see if this was working. And then we will get into the next phase, that is observability. So we try to reduce the resource consumption because of this limited CPU and memory that couldn't handle additional load for the monitoring and visualization tools. We're running version 1.13, and you just get kube control, get pod, Stackgres, and you have here things running. Challenges to get this up and running. We had a lot of compatibility issue. Running Stackgres on ARM-based Raspberry Pis requires adapting the software for ARM architecture and fine-tuning the Kubernetes settings to accommodate the limited CPU and memory resources. The default configurations often assumes more powerful x86 hardware, so be careful with the adjustments where needed if you want stability and performance. We also improved the storage, so we implemented ZFS pool for shared management and configuration of the ESCSI volumes for a reliable and high-speed access. Due to the Raspberry Pi limitations, we offloaded intensive tasks like the Kubernetes control plane and the NAS server to the two AMD 64 desktops that we just showed before. It was a way to ensure that the cluster remained functional and at least a bit performant. Software compatibility. To overcome these challenges, we had to recompile the Envoy component for a better performance. Now, everybody can get, because thanks to Stackgres, this is public for everybody. So now you can use the Envoy component in the Stackgres solution using ARM. Also, for networking, we wanted and tested Cilium, but we encountered failures that will require alternative approach. Initially, ESCSI targets were configured using TGKey, but were later switched to Leo, the Linux input-output target. The idea was to try to improve the stability and the performance, but the whole entire process involved extensive trial and errors to fine-tune the setup. It was not a single shot. It took us few weeks, I would even say a month and a half, to get everything working and sorted out all the compatibility issue. Despite the challenges we achieved, we were able to successfully deploy all these Stackgres, overcoming the whole architecture limitations and integration to build this functional environment. How it started and how it ended can be reflected in this picture. We were really eager to start the project and very excited, but we end up, let's finish this as soon as possible, let's move to something else. A lot of headaches, a lot of hours and nightmares running this whole thing, but it was fun. Usually learning the hard way is the best way to get things done. Let us show you just a quick demo on just getting the patroning topology and how you can see all the workers. In the demo, we run the following command to display the whole topology. Patroning is an open source cluster management tool that automates the deployment and the failover of high availability Postgres clusters. Let me just hit here. And this command will provide a clear view of the cluster setup. It will show us the node that acts as primary, which ones are replica. In our case, that we had 20 workers, each with its own replica. And now comes the fun questions. You say, what happens with the whole observability thing? We found many key problems here. We had resource constraints. We had limited CPU, memory, even disk space on each Raspberry Pi node, and there was no space available to install any monitoring agents or exporters. We also had this bandwidth limitation of 300 megs that become a huge bottleneck, and we had high data volume from metrics collection that was overwhelming the whole network. Last but not least, we had inefficient observability data flow. We were trying to send directly the metrics from each node to AWS cloud, and it resulted in high latency, excessive bandwidth consumption, and increased cloud cost for the storage and transfer. So we were trying to find, what are solutions that could help us minimize all these problems? We look at defining our own custom metric collection. We could use a lightweight Python script to collect just essential metrics, CPU, memory, disk, and network using the PSUtil tool. We can consolidate and batch data at the gateway node, one of the servers that we were using, and compressing the whole payloads before sending that to the cloud. From a bandwidth perspective, we could reduce the sampling frequency, collect metrics every 60 seconds or even 120 seconds, 1 to 2 minutes. We could use a lightweight data transfer protocol, a MQTT, with compression, and we can send only aggregated data summaries instead of the raw metrics. And also, we could implement some edge processing to analyze and filter metrics locally before the whole transmission. And we could send only critical alerts or anomalies to the cloud for further action and remove anything else there. So scaling observability solutions for a large number of Raspberry Pi nodes is not feasible with traditional exporter like Prometheus node and so on, using the 3B plus cards. Probably if you use modern ones, you can feed the exporters in a better way. This is how it looks, the whole thing. We had couple of scripts that we were using. One is the metrics collector that collects the CPU, memory, and the network metrics. It will compress the metrics using gzip to minimize bandwidth and will send metrics every 120 seconds to the gateway. Then the gateway script will receive all the compressed metrics, decompress them, store them in a list, and it will aggregate metrics every 5 minutes. I will send those to AWS CloudWatch using the CloudWatch API. Note, if you're going to use AWS, you need to install both of 3 AWS Python libraries in the monitoring gateway for the AWS integration. You could set up alerts in CloudWatch for critical thresholds, things like over 80%, just send me alerts, and visualize all those metrics using Grafana by connecting CloudWatch as a data source in the manage. You have 2 ways of doing Grafana, by the way. On AWS, you just can go and manually install it on your EC2 instance, or you can use just the managed service to make it work. Here it looks here are the Python scripts used for both the gateways and the node. We will use our own AI assistant to explain the code that we have here. As you can see, It will create a Flash server, install the metrics, will accept post requests, decompress the data and store metrics that we were talking about, CPU, memory, disk, and do the CloudWatch integration out there. There's some background processing happening, as you can see there. We'll send them to CloudWatch, logs the results, and even it tells us how we should look the output there. If we go to the metrics collector, as you can see here, we're collecting different metrics and sending to the gateway. We'll ask also to highlight this code and explain it in different sections. It looks at the different things we have. We can ask them to improve, by the way. Maybe our function is not, I'm not an expert programmer, I just do things for fun. But maybe you can ask your AI to improve the quality of your code. And here we just configure the gateway API, and it will include the error handling and the main loop on the whole thing. Bit of examples of how the metrics looks like and how the scripts takes that it's appeared to be a larger monitoring system where multiple nodes will send their metrics to the gateway compressed. So the results here, frequent metric transmission from all these 63 Raspberry Pi nodes saturated the 300 megs shared bandwidth, causing latency, packet loss, and a very huge degradation on performance for other workloads that we were running. Also, high CPU overhead we had there. Processing this whole thing in compression was not a very good idea. Probably have been better just to send raw data, but also we had congestions on the network and let the server to compress and do the whole thing. We had some gateway bottlenecks, so centralized aggregation on a single gateway leads to processing delays and scalability limits with risks of getting drop or delay metrics under a heavy load. And we had also an unreliable observability. So resource constraints result in inconsistent reporting, gaps in data, and potential cardinality explosions, which makes our dashboards and alerts less accurate than action. So this is a bit of how we went with the whole thing of setting up a 63 Raspberry Pi cluster. We had some overall lessons learned out here, mainly on the importance of planning. It might take much more time than what you expect to really design how you want, not just the hardware, how you want the software, but also the adaptability, how we can merge both software and hardware to make it work as a single unit. Many things that we had to achieve on the journey to make this work, but also collaboration, because this is not just Jorge and myself doing the whole thing. We got people from Stackgres helping us on validating some of the configurations, helping us with the compiling of the Envoy proxy, and we brought other experts to take a look here. But moreover, experimentation. If you want real production workloads, you need to have a distributed storage and other kind of updates that we didn't consider here because this is a work in progress so far. And when I mention work in progress, we're not stopping here. It's been like 7-8 months of project, but we want to optimize Linux. We were going with Ubuntu, probably try other alternatives like Rocky Linux. Also benchmarking a shared cluster and have a real world application running on top. Probably we will need to change most of the hardware to go to more improved Raspberry Pi, or even just try another nodes like the Orange Pi, but mainly also how we can fine tune the Kubernetes thing. And the best part is how we can bring AI to the edge. The idea is that we can have a chatbot for Stackgres incident support. We want to train the chatbot using all the errors and things that can happen in our cluster to provide a solution for other customers in the near future. And how does the near future look like? Superclusters can be used to train and deploy lightweight machine learning and AI models at scale. So, for example, the Raspberry Pis could process smaller datasets for tasks like image recognition or natural language processing, which can enable a cost-effective edge AI solution. But by bringing computation closer to the data source, Raspberry Pi clusters can serve as a powerful edge computing platform. They can enable real-time data processing for cases like smart sensors, video analytics, and autonomous systems, which can reduce the latency and reliance on centralized cloud infrastructure. And last but not least, IoT management. I think that they can also act as hubs to manage large-scale IoT deployments, and they can handle tasks like device orchestration, data aggregation, and monitoring. The ability to process and analyze IoT data locally makes them ideal for smart cities, industrial automation, and connected environments. And with that, thanks for joining this session. Here are our handles if you want to follow up or just get in touch. Let us know if you have any questions. Just throw it out there and we'll try to solve it. Thanks very much. See you in the next one.